How are you getting on? Our name is Team Croft, and my name is Pat. This is Neil, Kieran, and Daniel. And our aim was to build a mechanism to predict a particle and be able to predict its range mathematically. So we decided to build what you can see behind you, and just a little bit of a rough sketch here. But first of all, we're going to use springs. So we had to find out how was the decay value for the spring using Hooke's law. So basically, we just got an ordinary spring. That's natural length. We put a mass on the end of it. We got the difference. So this is the length, L minus LO. So we fed this back into our formula to get the K constant for elasticity over the mass, and we got our answer. So yeah. So this is actually the work over here. So we actually looked with overall value with 479.9 newtons. So I'll hand you off when the boys out to say something. I think you don't know. I've already gone to here before. Which? Well, I've got Farrell's force. Just the whole big force.
Oh yeah, they wait to find the speed of the ball. See that velocity of the ball is going to move off it. So we're getting into our problem here. Yeah, we got taking K constant, we found the mass of the ball, found the mass of the launch mechanism, like the launch pad or whatever you want to call it, and we fill it down and got at 5.42 meters per second. So that's the speed the ball is leaving the ball at. So then we fill this into our formula here to find the projectile, the range, max range of the projectile. The range equal to velocity squared sine 2 theta. So the sine of the angle, sine twice the angle, divided by g. So we fill that down on, and our max range is 3 meters. So then we come back here, we have to find what kind of losses due to friction and other losses we found, and found a total loss of 5%. So we got 5% there, and we got 2.83 meters as our max range for the projectile. And that's an angle of 45 degrees. So then we can just feed in whichever angle. We can feed in the range. I think you're giving us the range, we put in the range, and we can form that. We're going to find the angle to set the yoke
up. Can you say a few words about the other alternative that you looked at?
The other alternative we looked at was based on a seesaw model, which is commonplace in most of the school play playgrounds. And there has been several examples of this through the centuries as well, with weapons such as trebuchets, and also in industrial use with wheelbarrows moving substances around. So what we did for our model was we proposed to drop a weight onto a seesaw on one end, and we'd have our ammunition on a cup, and the moment the weight would hit, it would move the ball, and the ball would take off when the board would hit the ground, as can be seen.
Do you want to bring that over just so everyone can see?
As can be seen here. For the max thing with this thing, we had to look at all the energies involved. For example, the potential energy of the weight being dropped would have an effect on the speed of the ball's departure. So we got the potential energy and we converted that to kinetic energy. And upon impact of the weight with the lever, you would have to use the equation for conservation of momentum. And after getting the speed in of both the weight and the lever on one side, we had to transfer that using moments to get the speed of the ball when it would leave. But yet we would have to account for losses in friction and air resistance and the gravity. And we only had one variable in that, mass of the weight that was dropped. I think, and we kept all other factors constant.
Why did you choose one over the other?
The calculations are more doable, really. Felt it was easier calculating and more predictable. Much more predictable.
It's more reliable with the springs.
To be less margin of error.
Yeah.
A lot less.
And it's a lot safer as well than dropping the weight down every time as well. So,
Do you think having done it, having built your preferred model, that those reasons have held through?
so yeah.
Would you like to talk about the losses again? Where are the losses in this system?
The loss.
Friction, really.
Friction. But we have a stick, our elastic friction energy here, which stands on kinetic energy plus losses. We lost probably friction, gravity, air resistance, and if we're actually putting it back by hand, if it weighs a little bit, you might lose a little bit of power. You're not getting the full force directly. So
But it's only 5% really, so
only 5% really the velocity kinetic energy, so in distance.
How do you know it's 5%?
Well, we fired it at 45 degrees. We got what we should. It was 3 meters. But we actually fired it in a ballpark, plus minus or 2.835 meters. It's 5% less in distance. So it's about 5% loss of kinetic energy.
How many did you test that?
We did took several shots. Yeah, several shots.
So on average.
Yeah, several times.
Over different ranges?
Yeah.
No,
At different distances?
Well, but even the minimum range was done a few times as well.
Like the question is, like, is it the same percentage loss at a short range as a long range?
Yeah. It was very, very tight anyway.
Within 1%.
So based on the range of 2.25 meters,
Okay, from 2.25 meters, as you put it in here, sine inverse, this basically switch around with this. We bring 2.25 meters here, so we can actually get around it, which we can set at to launch. So if it's money, you can start putting that in maybe. Calculator. Yeah. 2.25 here.
in terms of the velocity calculation, can you just confirm what masses are you taking into account? In the,
The weight of ball, the weight of all apparatus connected to the spring is everything except the spring.
and how does the weight of the apparatus compare to the weight of the ball?
I think it's actually a bit heavier than the ball.
Yeah,
It's the weight of the ball, isn't it? With 3
Ball was
times.
0.023.
Yeah,
With the whole apparatus 0.13.
yeah.
So significantly.
Yeah, it's a little bit heavier.
Had you initially allowed for that?
Not in the very beginning, no. We ended up with a range of 20 meters nearly, so.
So could you make your machine more efficient?
Fine further.
Far further, sorry. Or
Quite further if we extend this.
Pull the spring back more.
Back with the same spring and the same
Lighter
ball.
material.
Yeah, if we extend the spring, we can allow the force. This is the extension of the spring, otherwise it's 0.
Mhm.
So we make this bigger. The larger K, larger force.
Is K different? If you make
Okay,
that?
same.
No, K is the same, but if you want to apply this in, it's going to be bigger.
Okay.
You know, so
Does that make it more efficient though?
Wait, just have these
more
light-
accurate.
Like more
Yeah, light
efficient?
materials.
If you
Lighter
extend
material.
the spring
We polish
further,
the platform.
I don't think so, no. The springs may get damaged. I don't think they'll be enough.
but extending the spring further will throw the ball further, but does that make the machine more efficient?
Not
I
really.
don't think so, no.
You put more force, so.
You put more energy in.
Yeah, yeah.
I suppose the only way is
What
to
would you do
lighten
to
up
make
your
it more
materials. Like the launch pad, make that lighter.
Okay.
Polish the surface on which it's running along as well to reduce the friction.
okay, so do you have an angle?
Yeah. 24.35.
24.35 degrees. Now, are you going to vary that in any way to allow for those losses, or how are you going to allow for the losses?
We'll multiply by 5%, say. Yes, maybe only 5% less. What on all the
Or we add to
the range?
We add 0.5, that's 95%.
Yeah, yeah. So that's 5% is 2.5, so it's
Get 5%.
already said that, so 5%. Concept of. Yeah. You alright, Tom?
Wow!